Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and here's another short video. This time I promise it will be really short. So today we're going to look at this stacked 4-pole, 4-DualPole kit. It's still a 4-pole even though it looks like there's many more poles on it. But first I want to again make a plug for my other video series, my real superhero, historical superheroes video that goes over what a real superhero is, and I encourage you to all watch that video. And I will be doing another one this week that gets to the most important thing in life, the most important secret that has been overlooked and misunderstood. I do ask you to look at that video coming up. Anyway, let's start off with this video here where we're going to be looking at this particular I'll probably make this available as soon as I figure out a couple of details. For example, these rods here, these bolts, and get it all figured out. I've had to cut these from Home Depot. I had to get these, and I would like to get better ones. These ones are magnetic, so they pose a little bit of a drag. Not much, the magnets are pretty far away, but I like to keep that all non-magnetic stainless steel. Not all stainless steel is the same. So when I use stainless steel, I use the right types, and there's a couple of variety that will work. My shafts, set screws, and all the bolts and nuts are always non-magnetic type. So what we're doing today, what we've done is all motor coils here. Now we're not running them as motor coils, we're only running 4 motor coils. And what I've done here is I've got 2 motor coils on either side here, and then on the bottom these 2 are running as motor coils. There's no trigger coil here. This is all MOSFET Hall switching circuit. And what I've done is, from my other, you've probably seen pictures of my 3-stacked system, and that was an experiment that I was doing, which people are trying to copy. And what I was doing there was simply showing the relationships of the generator coils. If they're far enough spaced away from the magnets, they pose no drag on the magnets. And they still can put an output out. Now it's not very much, so it's not really worth it to do it, but it was something I wanted to show. So now, in this case, the limitation of doing that actually was I had all generator coils on the top, all on the bottom, and then just the regular 4 motor coils and 4 generator coils. Now the great difference between the coils on the outer sides were that they hardly produced very much. And that wasn't just because of the gap, but because they were not close to any motor coils. So this is the whole purpose of this kit, was to have the motor coils in close proximity to the generator coils so that the generator coils could pick up some of that lost energy, so to speak. So you're pulsing a coil and it's going to be picking it up beside it. So there's a great difference in the relationship when we do that between just having a regular generator coil by itself and being beside a motor coil. There's a lot of dynamics going on there. Even though they're not terribly close, there still is a ½ an inch apart from each other. So it's not really induction that's doing that. Now we're not, running this at high voltage either. right now. Now, this particular model, I want to run it at a higher voltage. In this part of the video, I'm going to run it at 12 volts first, and then we'll go up from there. Once we clip this little red wire, and this little red wire is only going to stay at 12 volts while we add more batteries, so that we can push this thing really hard. Now, I tried to do this with one of my older motors here, but all the ones I have left were over drilled in the hole size, so this one was on my motor here for quite a while, and now it's really spinning so I can't use it anymore. And so I had it in there, and then it was just spinning around, so I needed to go to the aluminum rotors that have the set screws in them. Now what I did, for those of you who want to do this, I had to actually, or I didn't have to, but I did grind this down so it went right to the set screw. And I think next round of rotors, that's what I'll do, is I'll make this hub even smaller, which will save me money on the cost of it because it's less material, but also now we can stack these and not have such a big of a gap. Now initially when I did my gaps on here, they were further apart from the rotor. The rotor was further apart from the coil. So now I have them, I cut those little spacers less than 1/4 inch. So it's about, yeah, it's about a 1/4 inch, just a little smidge less than a 1/4 inch from the flange part of the spacer to the other end. So I'll cut them, I'll put them on the shaft like I showed in the other video, and just cut them, because I can't get them in that particular size as far as I can look right now. So anyway, so the gap between either rotor is about the same. Now there is a little bit of a space on this side of the rotor as well from the magnet. So, but it's not that much of a difference. So now, we'll probably make that equal on either side in the next round of orders. So anyway, what we have here, like I said, is the 3 generator coils on one side and 3 on the other, and then the 2 motor coils on either side. So now what I noticed, a couple of things to mention, and this is what I was just talking about. When I run this right now at normal speed without loading down the generator coils, what we have is the 4 coils right beside the motor coils are putting out 2.67 volts. And these are 23 gauge wire, so all of these are the motor coil. And what I've done to distinguish them from each other is I've turned the motor coils upside down like we normally do, so that we have the north pole of all the magnets facing up and all the rotors. And of course, the bottoms of these, where the flange is, when I run them the normal way, the bottom is a north pole facing upward. So don't get that confused. I had to flip coils around and circuits around for a friend of mine recently, because he had done them all upside down. Now, so what I noticed was 2.7 volts around on the coils right beside the motor coils, and then these outer coils here were only 2.4 volts. So that shows you right there what I'm talking about. We are collecting some of the energy into the generator coils when they're right beside each other. So like I said, what we could do is make this an 8-coiler and just make these two motor coils at any time very easily by taking the wires out, putting them to another circuit, or whatever. We could make all of the coils motor coils as well. This thing would fly. In that case, we would really want to make a bigger shaft and load this thing down. Mechanically, that would obviously be the purpose if we were going to do that. So in this case, I've done the opposite. I've added double the generator coils than normal. So we have, instead of 4 generator coils, we have more than double here. Hold on a second. 1, 2, 3, 4, 5, 6. So we've got 12 generator coils this time instead of 4 generator coils. So we're really loading this thing down. Now I don't have, the particular shaft I used was used up here. I don't even have any excess. So I'll put another shaft in there if I want to extend this out here and run a load off of it. I'm going to push this thing to 48 volts. I've got everything that can do that. Well, all I have to do is replace this one wire here, cut it, and go to 12 volts of the primary instead of, when we go up in voltage 24, 36, 48, I don't want 48 or 24 volts going to my gate of my MOSFET. Now this particular MOSFET is not the one provided in the kit. The one in the kit is a 40 volt. So I had to replace that with a higher, this is my really big MOSFET, a $13 MOSFET that is 2500 watt. So it's a 500 volt, 100 amp maximum MOSFET. That doesn't mean you can run 500 volts at 100 amps. It means that's the total amperage that this can put out and the total voltage. And you divide the two by 1500 to get your volts and your amps maximums. I would never run them at the maximum amperage, and if you go above probably 50 watts, you definitely need a heatsink on there. Anyway, we'll have a different MOSFET in there in an upcoming version of this kit. That is, by the time this video gets online and you order it, I'll be doing that, probably with the MOSFET driver as well. The new MOSFET driver, which is a little bit more efficient. So higher voltage FET and higher efficient gate driver on the MOSFET. And now going back to this whole purpose here of this video. So we've got 12 coils in series with each other from top to bottom, zigzag, series all the way around. And we're going to look at that in a second. And everything else is the same. It's just double stacked. And then we have it carefully measured between these two plates here so that we're not imbalanced. Now I did take out one of the, there's one less bearing, because in this plate right here, I took out that bearing because it's impossible to have this perfectly lined up, even though it's perfectly machined. And any kind of difference in any kind of bend in the shaft or whatever creates a problem when you have all 4 bearings in line. So taking out this bearing makes a big difference. It's not needed, so I don't need a spacer as well there. And that one really wouldn't have room for a spacer in there anyway. So there's no need for that. The shaft is going to be fine. I've got this rotor right beside the bearing there, and it's good and tight. Guten tight is my fake German word. Um, so it's nice, this turned out really nice compared to my other one where I actually drilled the holes and then they gave me the wrong size shaft and what have you. So this has turned out really nice. And so now we're going to look at, I let these batteries discharge a little bit because they were running for a little while. This is the charging battery. And this is the input battery. $12.39, and that's been under load for a little bit. So we'll leave this connected here for a moment. So I noticed in my other video that I couldn't see sometimes the screen here. So tell me if you can't see this. Oh, well, there's nobody there to answer. Okay, so let's look at this now. This is going to be drawing anywhere between 1 amp and 1.5 amps. Now at startup it's going to draw a lot more, and this doesn't self-start because it's under quite a bit of a magnetic lock here. There's no way for me to make this self-start, which does make a big drawback on this. The way around that, and the same thing can be done with these big motors here, the way around that is to actually mount another coil and not right in the center, but off to the, and then just pulse it really hard to get it going if you want it to self-start in that sense. Again, everything's the same with this Hall sensor, which is triggered by the South Pole. Now, I don't have generator coils in the same way. In fact, I'm putting this on the motor coil, which makes a difference on the Hall. And I found that, let's see, it was influenced in a different way on the middle plate. Well, actually, that was when we were running the plastic plate. So, all right, so let's get started here, and we don't really need to look at the scope. I suppose we could turn it on. I haven't bothered here, but it's not really my objective to focus on the scope as if it's some kind of important instrument. Now, let's look at, we could look at the sine wave on the generator coils too if we wanted to, but so let's get started here and turn my amp meter on. So what are we at? 12:15. It's coming back down to where it was. And now we're gonna, you notice I've got pretty thick wires on here. That's what I want to do, not so much for the input, but the output wire. These are 14 gauge wire. That will probably come with the future kits as well. You can go up to 3/0 wire on it. I'll probably show that, show the difference. Now somebody just, from my last video mentioning all that, somebody just posted the difference between going with the clips and going with the push-on terminals, and made a big difference, taking out the resistor for measuring the amps, and they noticed the difference in performance. Well, that's very good that they are, some of you are listening and experiencing the difference already. So in this case, 14 gauge wire is all right. We're not pushing this very hard, but like I said, the bigger the load, especially on the trigger coil, the more the efficiency that you're going to get out of it. Alright, so let's give this a twirl so that it starts. So far I've got 0 amperage. Anyway, let's look at the amperage. It's 1.5 amps, 1.4, 1.3. I'm positioning the hull. I haven't decided where to put it exactly. Oh, we are under load here. Now what I want to do, get this thing up to speed first before we do that. So you can see we got the double pulse going there. And that's at 50 volt divisions. That's a pretty good pulse on there. So it's only 1.17 amps right now. 15 volts, pushing this thing up real fast. Now, let's look at a couple of things here. So we're at 12 volts input. We're hitting this thing really hard. This battery. This light is quite blinding now. This is very, very bright. It's at, but you'll notice that we're still, okay, we're loading down the motor a little bit more by another, it's 1.3 amps right now. And we're charging just as good, so 15. Alright, so now what we want to look at, so this is representing right now the same amount of energy because I have bigger coils now. Oops. Sorry. I gotta look into the camera here. So this is representing the same amount of power that I'm running the motor off of. 12 volts at 1.3 is definitely what this is outputting right now. And if you run different types of loads, it will be different. So you got to find the right type of load to run the system on. Now, like I said, I want to make this thing run at 48 volts because I want to make this a 200 watt device, right, that we can run these motor coils at, if we do 48 volts, my idea is to run it 48 volts at half an amp per coil, motor coil. So we have 4 motor coils, so that's 2 amps times 48 volts. Well, no, that's 1 amp at 48 volts gives us the, yeah, that's what I want to do. 1 amp at 48 volts. I was going to do 100 volts at half an amp. That's what I was going to do. But then I realized to find that 115 volt inverter is not easy for everyone to find. So I decided 48 volt inverters are easy to find. So if you do 1 amp, which is really the maximum that these coils should run before they get too hot, then, and there is some airflow, but it doesn't really reach, it's only on the other side of the rotors, of the plates here. But anyway, we have 16 volts going on here. So if we run this 1 amp per coil at 48 volts, or we could do 8 motor coils and then run it at half an amp each, if that's what this is going to require. Definitely don't go over 1 amp on these coils, because the rods will get hot before the outside of the coil. So you got to watch that, because it can melt down on you. And then you'd want to put fuses on those. So again, I only have the positive probe terminal on the center terminal, instead of using the ground. Which that would show you. Not much of a difference. Anyway, it's not important. Okay, so now what we want to look at is let it get back up to speed. So notice that we're at 16 volts on this battery, and soon it's going to be off gassing on me if they go too high. So my amperage, of course, is going down as it's speeding up. It's not, the generator coils are not under load. So now what I want to look at, I'm going to show you again, is, okay, it's still climbing a little bit. When it gets to 1.17 again on the input amps, then we'll be good to short this, because I want to wait to show you something here without touching anything else. So it's definitely posing more of a drag on this than normally, because we have the magnets in pretty close proximity to the coils. So we're about 1A4, still rising a little bit. I moved this around. Still coming up to speed. But what I want to do now is short out the generator coils. Well, first of all, let's look at the voltage. So we're at 35.7 AC, 1.183 amps, 1591 charging battery. Now I'm shorting it, and you heard it speed up. The amps are dropping. Oops. I didn't keep it connected there. The amps are dropping 1.15 and lowering, speeding up faster and faster. Of course this, because the amp draw is lowering, the charging rate is slowing down, but it's speeding up noticeably. We're at 1.125, 12. So it's going down to about probably about 1 amp, 1.1 amps a minute. So it's speeding up. So the coils are essentially becoming non-existent in the magnetic path. They're closed looped to each other, shorted. Now if we get the right kind of load on here, then we can actually see a similar result, which I've shown many times before. So we're at 1.1, pretty much stabilizing right now, at 1.1 amps. So we've come down quite a bit, still lowering. So now what I want to show you is we're going to leave one side connected. And so what I have is just a terminal strip here. So now we're going. So we have, starting with the one side, four volts, 7.5, 11, 15, 19, 22, 25, 27, 29, 31, and 34, and then of course 36.3, around there. So that is, so I went back up to 1.178 without shorting the coils. And of course the charging rate went back up a little bit. Like I said, once we run the load here, it's going to draw more. This particular load draws more energy. Loads down the motor about 200 milliamps more. But the good part is it draws, it charges more too. So that's where it's nice. In a regular motor, of course, you have no recovery. So, but here, it's proportional, the recovery, the charging, battery correspondingly charges faster. So 1.357, this battery is more fully charged, then this would be running a little bit faster, of course. And like I said, once we go up to 24 volts, it'll be different. So I think that's what I'm going to show for now. I may show more if I go up to 24 volts right now. So let's turn this off for a second. Let's Just let the voltages stabilize. And then what I will do, so you can see the voltages are bouncing back. 1323, that's definitely going to come down. And then this one is going to go back up. So let's get some other batteries going here for my next experiment. So what we'll do is keep that one there. This will be another input battery. Because what I want to do is run this at least 24 volts. And then we can drive this whole thing. A lot harder. But it's just more of the same. Right? So 1230, it's going to continue to bounce back up more and more over time. Here. And this one, 1290. So this one's going to come back up, that one's going to go back down, we're all good. Here's part two. Part two of this video. We're going to run now 24 volts. Now the important thing to notice, the only difference that I've made in the circuit is we are running this red wire going to the opto board. Instead of going back to the main input, which would be 24 volts in this case, and I did put a diode in here. I usually have that in the kit now, so that if you do connect it to the wrong terminal, or if you connect your input terminals backwards, you won't blow out the hall, which is what people do. So I put the diode in there now. So now this is going to go only to 12 volts. That's the key. It's hard to find the regulators. Well, this is one reason why I'm staying with 48 volts maximum on this kit rather than the 100 volts, is because it's hard to find the voltage regulator that's under, well, it's 100 volts for one. And then the gate drivers and all that, we want to keep them at that lower voltage. So I'm going to run this going from the negative terminal to 12 volts. So if we start off with a 12 volt battery, we go to the other end of the 12 volt battery, the positive side. Even though I'm putting them in series to another 12 volt battery for 24 volts, I'm not connecting it there. That would be 24.6 volts right now. So now we're going to run this LED. Probably going to be damaging it at this point. So we have 24.6 on both battery banks, because some of these batteries are discharged more than others. This particular one that I've added, yeah, 12.3, so they're about the same. So now we're going to get this thing started. It peaks out around 2 amps. Now what I just said about not running this above 48 volts, you can do that with the trigger coil. So that's what's nice about the trigger coil. Now I'm not using the thick wires again because I'm just going to show this basically running here. So I'm violating my recent YouTube comment where I said I want to run thicker wires all the time. Be a good example to you folks. Alright, so let's get this started and watch this thing rip. Come on. So starting off with about 3 amps there. We'll let it get up to speed. So now you can see the spikes. This is 100 volt divisions. You can see it go negative too. It's a good fat. So we're at 1.8 amps. Really charging this thing. 30 volts, 30.1 volts, 31 volts I mean, and climbing. So that should get up to 32 something there. So you can see it does all the same thing. Now this is probably going to damage my LED. This is a 100 watt module here. And yeah, they come in different qualities, that's for sure. So now that is really bright and it's hot already. It's just blinding me, I can't see. So now we're going to be really pushing this battery, 32.2 up there. I'm not sure if this can see it or not. I'm not going to blind the camera with that light. You can see my face all lit up now. Anyway, there's the motor all lit up. We don't need any more light in the house, it's bright enough now. So 1.95 amps, you can hear it resonate. So when I take this off, it's at 1.8 amps, amperes, 32.8 charging. And then of course we can short it out. Still going up to speed, but when we short it, it's going to go drop the amp draw even more, speed this thing up really fast. Now we're approaching Mach speeds. This is scary. This is a lot faster, of course, than even the regular single stack kit. And this is where I definitely want to keep this thing loaded down. So now that's going to be really bright. So now if I disconnect this, that turns the power right off right there. Now you can see the generator coils are still putting out. Oops. But it's loading it down. 26.3, the voltage drops. This is going to come back 24.6. We didn't run it very long. And my amp meter has been off. It's sitting at 1.3 or 130 milliamps. So I always have to zero this out depending where I place the amp meter. So all those readings that I was saying were 130 milliamps higher. So anyway, there you have that, and all we have to do is add 2 more batteries. We're at 36 volts. So let's try and do that here. this time that LED is going to have some serious trouble. So we're going to add this battery here, which is not charged. It's 10.4 volts. So we'll charge this battery up. Always connect your charging battery first. And then we will add this little guy here. I think he's still got some charge in him. 12.7. Now this is only a 5 amp hour battery. So we'll stick them right here. I'm not sure if I'm going to go all the way up to 48 volts. Makes you nervous, you know. Especially when I don't have a load on this thing. Now, again, all it takes is putting this wire 12 volts. Yikes, this is scary. Alright, so we're at the right voltages. And let's put our voltmeter in. .3 volts, 35.9, and let's disconnect that for now. I do have another bigger LED. It's for higher voltages. However, I should have another bridge rectifier across that. If I don't, I'll blow it out. So if I disconnect this bridge here, I can use it. So what we'll do, this is a much more powerful bulb. And we'll use these here, if we get it all right. Not exactly sure of the continuity there, so let me run this for a second. Okay, so that's the negative wire. I know I'll definitely blow out that bulb if I try and run that directly. So now this will be very blinding. This is a 150 watt bulb, and it's a really good quality one. So what I'm going to do is leave it disconnected first. And then we'll add it later on, once this thing starts going. So let's get our voltages all lined up, or voltmeters. Alright, so we're at 37.3. And this thing is going to take off if it doesn't blow out my fat. It may blow out the fat. I should put a heat sink on that. I do have one there somewhere. Could probably put that on fast. So we're at 2.9 amps, and this wire is not making it. This particular wire is melting on me, so I will use that here. I could see the wire actually start to shrivel up. So I knew it was a cheap wire that couldn't handle the current, or whatever you want to call it. Alright, so let's do it again. Let's zero this thing out this time. $35.9. So we're at 2.8 amps, 2.7. This thing is going to fly, and I'm kind of nervous. I'm going to put a box in between me because this thing flies out on me. It'll go right through me like a bullet. I suppose this box isn't going to stop it. So we're at 50 volts. The spike's pretty high. We'll change the spike down, or we're already at the limit. So we're at 35.5 volts, and we've got some heat going on here in this wire, and probably going in the FET. So now let's do the alternate. Let's look at the voltage on that first. So I'm pretty good here. I'm not going to short out those coils. Kind of nervous running this thing unloaded. So the voltage at 36 volts is 73.4 AC. So let's look at this under load now. So we're at 2.5 amps, and we're going to look at the voltage AC. Can't really focus, the bright light is so bright. So we're at 40 volts on the coil under load. 40.6 volts. We're charging at 50.8, and we're going back to volts here. And we're at 35.3. And this wire is a little bit warm. See these wires? The charging wires are important too. So anyway, we're doing pretty good here. It looks like I've damaged this. When I tried to run this bulb on my one light, it was damaged because it was too much power. So if I turn off the lights here, it is very bright. And that is it. Let's see if all these coils are good. They're all actually they're getting warm. Uh-oh. I just blew something out. So anyway, that's the FET blown out for you without a heatsink on it. What not to do. Yeah, that's hot. So anyway, that's the story of my life. Blown out parts. I touched this coil and the slight touching of it changed the performance, and then it went out. So let's look at the voltages now under rest, and we'll see where it goes to so that you can just get closure on this experiment. So when we go into the higher voltage here, you know, there's a lot more power available, and we have to be really careful. So we were going up there, approaching the one amp per coil, and this is where we need a MOSFET gate driver to limit the current, because we're getting too high up there. So I think really we're looking at making this thing run at safely. I mean, we were approaching 1 amp each coil, so I think we really want to limit it to ½ amp per coil is what because you have thermal runaway, especially if your temperature and the room temperature changes. So the ambient temperature will make a difference, obviously. So I'm going to say let's limit these coils to ½ amp each, and then at whatever voltage, 48 volts. So in order to do this, I think what we would do is just make it 100 watt sections. And so we were only at 36 volts though. So the problem is there's no way to limit the amperage with this basic circuit here. As you go up in voltage, the amperage is going to climb as well. And then of course if you load it down, it's going to draw more. So what we want to do is limit that to ½ amp per coil. So if we want to add more coils, then we can do that. I'd say what we would do is we would run 2 sets of FETs if we want to double stack it like this. But at 24 volts it was holding out really well with this circuit. We don't have to use that big MOSFET, but we do want to have a heat sink on there. So yeah, me touching this motor coil over here, set it over the edge, either I added some capacitance to it or something, or whatever the case, or we just happened to hit the thermal threshold there of that MOSFET. So anyway, we're sitting at 38.5 roughly, and 37.1 on the input. And that will go back up, and that will go back down. Now there was one of my negatively charged batteries in there, so I should have had another battery instead. But so anyway, that's it for now. I think this shows enough. We can do it at 48 volts, but we would want to limit the amperage with a current limiting system in that case. So thank you for watching.